Okay guys, welcome back. We're moving to activity 20.1. We're going to be discussing the Pythagorean theorem. That's Coach Williams today, or Mr. Williams, either one, doesn't matter. So again, activity 20.1, Pythagorean theorem, we're on page 283. Pythagorean theorem you've already learned about. What we're going to see in this next couple of sections is kind of going deeper, right? You learned about it in middle school, a squared plus b squared equals c squared. I'm not really sure what it is about that, but I swear it's one of the only things that everybody remembers every time. Oh yeah, I learned that. There's all kinds of things that we learn that we lose. Pythagorean theorem for some reason sticks around. What I want to do though is we're going to kind of review the middle school idea, and then we're going to go a little deeper. So in middle school, you learned the Pythagorean theorem. Given a right triangle, the two legs of the right triangle, when you squared them and added those sums together, you got the square of the third side, or the hypotenuse. And so here was the original Pythagorean theorem: a squared plus b squared equals c squared. And then what I've done is I've solved for the other letters. So a squared equals c squared minus b squared, or b squared equals c squared minus a squared. Basic algebra, okay? And then understanding that what I would tell my students is nobody cares about c squared, right? When I ask you to find the hypotenuse of a right triangle, I don't want to know what c squared is, I want to know what c is. So just kind of a reminder that you actually have to take the square root to get the final answer. So if you're looking for the hypotenuse, you're going to take the square root of a squared plus b squared. This is the distance formula. In case you didn't know, this is where the distance formula comes from. And then if you're looking for one of the legs, you're going to be subtracting the other leg from the square of the hypotenuse, okay? So these formulas are very useful when you're trying to solve things. So let's apply that and let's solve these two triangles that are right here. This first one, I have 5 as my hypotenuse and 3 as one of my legs. So because I'm looking for a, right here, I'm going to have the hypotenuse squared minus the leg squared. So 5 squared minus 3 squared, 25 minus 9, that's going to give me 16. And then I'm going to take the square root, and I'm going to get a equals to 4. Hopefully you can follow along with that, and that makes sense. Just one more example. This time I have my hypotenuse is 13, and the other leg of my triangle is 12. So 13 squared minus 12 squared is 169 minus 144, that's 25, the square root of which is 5. Okay, and for that one, we're using that formula right there and simply plugging in the values. Hopefully that makes sense for you. Now, what I wanted to talk about is this example up here. Now this one, for some of you, like, oh, that's the easiest one, but watch what happens. This is basic Pythagorean theorem. We're going to have leg squared plus leg squared, so we get 4 squared plus 8 squared equals x squared. Okay, most of us are okay with that. We get 16 plus 64 equals x squared, so 80 equals x squared. And here's where it gets interesting. We have to take the square root of 80. Now, what is the square root of 80? It's not 9, it's not 8, it's not 10. Okay, we need to find the square root of 80, but we don't want to touch a calculator because that gives us an approximate answer. I don't want a decimal answer. So we're going to do what we call reducing radicals. And that's why I have this big list of square roots here in the middle of the board. We're going to talk about reducing radicals. The way you do that, the way square roots work, let's talk about square root of 4. What's the square root of 4? 2, right? Plus or minus 2, but we're not going to worry about the negative here. You'll deal with the negative in algebra 2. For us, we're just going to talk about 2. But why is it 2? Well, it is 2 because technically 4 is equal to 2 times 2. So there are multiple 2's there, all right? And the way the square root works is it's literally asking, hey, what number times itself equals this number? And so what you can do is when the 2's repeat like that, several different options. You can rewrite it as 2 squared, and what happens is the square root symbol cancels with the squared. Or another way I like to show it is maybe you write 2 times 2, and if you get 2 pairs of matching numbers, one of them can go out front. And so the 2 comes out front, leaving basically a 1 left underneath. There's always a 1 there, right? And so what you end up with is 2 times the square root of 1. Well, the square root of 1 is just 1, so the answer is just 2. Now, some of you are like, oh my God, you made that way too complicated. But I did it on purpose so that when we get down here, it'll make a little more sense. Okay, so let's talk about 5. What do you multiply to get 5? Well, 5 is just 5 times 1, right? So what number repeated? That's right, nothing. Nothing repeated, so the square root of 5 is just the square root of 5. That is already reduced. That is the reduced form of the square root of 5. Let's talk about 10. Well, what do you multiply to get 10? You get 5 times 2. What repeated? That's right, nothing repeated. Okay, so the square root of 10 is just square root of 10. This is where it gets interesting. Think about 18. What do you multiply to get 18? Your thoughts might be different than mine. Maybe you think 3 times 6, maybe you think 2 times 9. Doesn't matter, it's going to get us to the same place. I'm going to go with 2 times 9. What's repeating? Nothing. But notice what I have here. I have the 9. you can either notice that the square root of 9 is 3 and you can put a 3 out front, or you can rewrite this as its prime factorization and write 2 times 3 times 3. Notice you have 2 3's, and so you can rewrite it with a 3 out front and the 2 left behind. The square root of 18 is equal to 3 root 2. Okay? And that 3 comes from the 9. So anytime you have a perfect square under there, you can write it out front. For the same reason, for the square root of 25, 25 is just 5 times 5, so what I can do is I can just write 5. I don't have to show any work. Okay? So really what you want to look for are perfect squares. If you can find perfect squares that go into a number, then it makes it much faster. Now you're like, wait, what are perfect squares? Well, if you don't remember your perfect squares, make a real quick list here. Perfect squares are going to be 4, 9, 16, 25, 36, 49, 64, 81, 100, yeah? 121, 144. My challenge to you is you should be able to do that all the way through 12 at the minimum, probably through 15 or 20, okay? Y'all are going to college. We talked about this in the earlier videos. If you're in A squared I, you're going to college. I'm sorry, but that's just a fact. There's no reason you shouldn't go to college if you're in this course. So, since you're going to college, you're intelligent. And because you're intelligent, it's not that big a deal to learn some perfect squares, okay? And so what I'm going to do is I'm going to look for these numbers when I'm working these problems. So 40, for example. Well, I mentioned 4. Notice if I write 40 as 4 times 10, well, 4 is just 2. And the 10 we already talked about stays itself. So 2 root 10. 96. 96 is a harder one. Maybe you don't know what goes into 96. Well, I know it's even. So I'm going to start with, well, I'm just going to divide out 2. Looks like I might need some room as I go down. So we'll go ahead and get rid of this. So 96 divided by 2 is 2 times 48. Now maybe you can go faster than me. That's okay. I don't mind. Go. All right. If you can do it faster, do it faster. I'm going to get 2 times 2 times 24. Oh, well that's 2 out front because I had 2 of them. So these cancel out and comes out front. And I still got my 24. What do I get? 24. 24 is 2 times 12. Okay, well, now I've got 2 square root 2 times 2 times 6. Oh, well, I got 2 2's, so I can write another 2 out front. What's 2 times 2? Oh, that's 4. Still got 6 left. I can try to go further, but notice these are prime. 2 times 3 doesn't go anywhere, so I have to go back, and this is my answer. The square root of 96 is 4 root 6. Now, if you want to do that fast, maybe you can notice that 16 goes into 96 6 times. If you can take this 96 and write 16 times 6, you can go straight here. Oh, square root of 16 is 4. Okay? So it just depends how quickly you can pick up on the pattern, how quickly you can notice the primes. Okay? 101. I picked 101 on purpose. It's a nice big number. When you start trying to factor 101, you're going to find out that 101 is prime. Okay? It's not divisible by 2, it's not divisible by 3, it's not divisible by 4, it's not divisible by 5, it's not divisible by 6, it's not divisible by 7, it's not divisible by 8, it's not divisible by 9, it's not divisible by 10. That is as far as I go, okay? Because 10 times 10 is 100. So if there was a number that there was a square root, or if there was a number that went into here, there would have to be a number at least less than 10. And there's not, therefore this is a prime number, therefore this one simply gets written as square root of 101. It doesn't reduce. 210, okay? Another math trick, if the sum of the digits add up to a multiple of 3, it's divisible by 3. 2 plus 1 is 3, so I know this is divisible by 3. If I know nothing else, I know it's divisible by 3. So I can do maybe 3 times 70. Well, maybe I know that 70 is 7 times 10, so I'm going to write it as 3 times 7 times 10. So 3 times 7 times 2 times 5. Well, did any of that repeat? No. So even though this is a huge number, nothing happens. I get square root of 210. That is the reduced radical form. Okay? I'm using these examples because I want you to realize some of them reduce greatly and some of them do not. So you have to take your time. Just because it's a big number doesn't mean it reduces. Just because it's a smaller number doesn't mean it doesn't. All right? So let's talk about 64. if you took your time, kind of like we did with 96, if you took your time with 64, you would get 2 times 2 times 2 times 2 times 2 times 2. That's how you get 64. 2, 4, 8, 16, 32, 64. Okay? And so every pair of 2's, you could write a 2 out front. Or 2 times 2 times 2, maybe you know that 8 times 8 is 64, and you just write 8. Either way, that's going to get you your answer. Okay, so that's how you reduce a radical. So if you see them if you see them asking for an answer in simplified radical form, this is what they want. They don't want a decimal. Okay, the decimal is close, but it's not right. All right, decimal is not exact, and this is an exact answer. Okay, the last thing you're going to need for this section is the idea of a Pythagorean triple. Pythagorean triples are whole numbers that work out with the Pythagorean theorem. 3, 4, 5 is probably the most common. 3 squared plus 4 squared equals 5 squared. Okay. A couple of the other two that show up a lot, especially on SATs and tests like that, is 5, 12, 13 and 8, 15, 17, and every multiple of those. Okay. Now here's the scary part. There are an unlimited number of Pythagorean triples. There are an infinite number of Pythagorean triples. Okay. We don't expect you to know all of them. We just expect you to know what a Pythagorean triple is and how to recognize it. So what you're looking for is when you work out your Pythagorean theorem, when you do this, you get a whole number answer. Okay, that would be a Pythagorean triple. All right. And again, here are some of the basic ones, and there are infinite number. Okay, so you just need to know those basic ones and kind of how to recognize them. So here's what I want you to do. We just looked at page 283. We kind of walked through a lot of the information. What I want you to do is actually go over to page 284. Yeah, 284. And I want you to work numbers 5 through 8. 5 through 8, okay? 10 minutes or less, yeah? Try to go kind of quick. 5 through 8, 10 minutes or less, and then come back to me when we'll talk about the next part.